Great. So yeah, in my presentation, I want to talk about federated self-supervised learning for vehicle perception, specifically in the domain of computer vision. And I hope that during this presentation, the term federated self-supervised learning will be more clear to you what it actually means. So we've heard that a lot now in the last two presentations, that modern vehicles, they are equipped with a lot of different sensors, LiDAR, radar, but also cameras. And these cameras, they collect a large amount of image data. And of course, we want to use this image data to train our computer vision models on it. And the usual workflow is that, okay, let's say we have a fleet of cars. These cars, they collect a lot of data through their cameras, and then we would send this data to a central server and train our supervised methods on this data. But as we've seen before, is that transferring all the data to a central server is not always practical and not always doable. That is because of the high data volume, which leads to high communication costs. And also storing the data is actually quite expensive. And we've now known, we've heard about what the solution for this problem actually is. It's federated learning. So via federated learning, we can train our models locally and then only exchange the model parameters between the server and the clients. And this reduces communication costs. So we have federated learning as a solution, but we also usually use supervised methods. But that comes with a new problem, which is labeling on the edge. So we all know that supervised methods rely on labels, but if the data is not gathered centrally, the data would have to be labeled on the car. So we would need the driver to, for example, draw some bounding boxes for a car on the data, and this is basically not possible. That's not really likely to happen. So we have this issue of labeling the data on the edge. So recently, self-supervised learning has become more popular, and it's an interesting approach to deal with this problem. The motivation behind self-supervised learning is that the need for human annotations has been a bottleneck in supervised learning. So self-supervised learning is an approach that does not rely on labels. And unlike supervised learning, self-supervised learning learns model parameters from data pairs X and X prime. And I'm going to come back into that in a second and explain how that actually works. But basically, since we do not need any labels, for self-supervised learning, we solve this labeling issue. And therefore, it's very interesting to combine self-supervised learning with federated learning. And the combination is then called federated self-supervised learning. So how does it actually work? The first step, and also the basically goal of self-supervised learning, is that we want to learn an encoder that captures useful features from the data. So imagine we have a lot of unlabeled data. In our case, this would be data generated by cars from the cameras. We want to use self-supervised learning to train an encoder on this unlabeled data that actually captures useful features from it. In self-supervised learning, then you have an additional step, which is you want to fine-tune this encoder on a specific downstream task. And I lied a little bit to you. So for self-supervised learning, you do need label data, and you want to use supervised learning in the end to fine-tune this encoder. But the point is that the hope is that this encoder captures useful features from this data. So we only require a small amount of labeled data for the supervised training on the downstream task. So how can we actually learn this encoder? So usually, the usual steps in self-supervised learning is that we have an input image X, and we want to generate different views X plus by augmenting this input image X. And then we want to learn an encoder that embeds similar images close to each other in the embedding space. So imagine we have as input image this car. We apply different augmentations on this car. For example, cropping, we rotate the image, or we apply some grayscale on this image. And now we want to learn an encoder that would embed all these images close to each other in the embedding space. Because no matter what color this car has, no matter how it's rotated, it should be close in the embedding space. So this is the simplified architecture that all the self-supervised learning methods these days follow. So like I've said before, we generate augmentations. Here we call them X1 and X2 from this input image X. And these augmented images are then input to an encoder F. And the encoder F outputs the embeddings H1 and H2. And now our objective is to maximize the agreement between those embeddings, which is equivalent to minimizing the distance between them. And we, of course, repeat this step for all different images we have. And at the end, we get this trained encoder that we can then use for downstream tasks. So here I want to just show that the learned embeddings of the encoder are actually useful. So here, self-supervised training was done on ImageNet for a specific self-supervised learning method, and then visualized in 2 dimensions. So we can see that this method actually embeds images of the same class close to each other in the embedding space. So what I've just told you, it actually seems to work. And then in our second step, we want to fine-tune this encoder on different downstream tasks. So here, self-supervised pre-training was again done on ImageNet. And then the encoder was fine-tuned for different tasks like object detection and instant segmentation. And what you can see in the bottom sim-sam, that's basically a self-supervised learning method. And if we compare the results that we get from the different downstream tasks to the supervised method, we actually see that it outperforms the supervised method. So basically the features that our encoder learns are very useful. So now if I come back to our automotive use case and the heading of my presentation, Federated Self-Supervised Learning for Vehicle Perception. This is kind of the workflow that I would envision for how this would be done. So we have our car fleet that collects a lot of different image data. And then we would use federated self-supervised learning to collaboratively learn this encoder from different scenes. And then we would, in a centralized way, supervise or fine-tune this encoder on the downstream tasks that we are interested in. So in autonomous driving, this would, for example, be object detection or segmentation. Exactly. So as a quick summary of this presentation, we've seen like the 2 different problems that we face. Problem 1 was that the data transfer to a central server is not always possible. This is solved by federated learning. And then our second problem that kind of results from it was that the labeling of the data on the edge is also not possible. And this is solved by self-supervised learning. So federated self-supervised learning is basically a natural way to deal with these 2 problems that I just mentioned. And then by using federated self-supervised learning, we can make use of this massive amount of generated image data and improve our computer vision models for autonomous driving. And as a result, enhancing safety for us, basically. If you got any questions, please feel free to ask. Otherwise, we can also take them later.